We are getting into solving systems of linear differential equations by elimination. It's important to note that for this lesson here, x and y, when they appear in equations, and z, when it shows up, are all unknown functions of the independent variable t. So when we see derivatives, they are dx dt, dy dt. They're with respect to t. Here we have a system of differential equations. It's two equations and two unknown functions, x and y. The equations are d plus 1 acting on x plus d minus 1 acting on y equals 2, and 3x plus d plus 2 acting on y is equal to negative 1. And just to remind you what the differential operator means, this first equation, d plus 1 acting on x, actually means x prime plus x. And then d minus 1 acting on y means y prime minus y. 2 is on the right-hand side. And remember, these derivatives are with respect to t. We're solving these equations by elimination, which means we want to eliminate one of the unknown functions, either x or y. And looking at this set of equations, it looks like it would be easiest to get rid of x. I'm going to number the equations 1 and 2. And if we multiply the first equation by 3, and then subtract the result of applying the differential operator d plus 1 to equation 2, then we're going to eliminate the x's. Performing these operations looks like 3 d plus 1 acting on x plus 3 d minus 1 acting on y is equal to 3 times 2. I'll just write it as 6 on the right-hand side. Minus 3d plus 1 acting on x minus d plus 1 acting on d plus 2 acting on y is equal to, it's minus d plus 1 acting on negative 1. I mean, that minus is multiplication by negative 1. So we can write that right-hand side as d plus 1 acting on 1. We can see that the x terms will subtract out. And we have 3d minus 3 minus the quantity of d2 plus 3d plus 2, all of that acting on y, is equal to, now on the right-hand side we have d plus 1 acting on 1. Remember, that is the derivative with respect to t of 1 plus 1 times 1. The derivative with respect to t of 1 is 0. We're adding that 1 that resulted from 1 times 1 to 6, so the right-hand side becomes 7. If we collect everything in the brackets that's acting on y, we can see that we have a 3d minus 3d. Then what's left is going to be negative d2 minus 5, because we're going to distribute the negative that's inside to the 2. So negative d2 minus 5 acting on y is equal to 7. I'm going to apply the negative to the right-hand side, and we have d2 plus 5 acting on y is equal to negative 7. Now, because this represents y double prime plus 5y, we can immediately read the auxiliary equation for the homogeneous equation in y. M squared plus 5 is equal to 0 is going to give us that m is equal to plus or minus I times the square root of 5. So the complementary function for y is c1 times the cosine of the square root of 5t plus c2 times the sine of the square root of 5t. And hopefully you're seeing that once we eliminate one of the variables, or one of the unknown functions, the rest of it reverts back to what we learned earlier in the chapter, including the fact that this equation in y is non-homogeneous because there's a negative 7 on the right-hand side. That's a constant, so yp has the form a. Its second derivative is equal to 0. So when we substitute into this equation, which really means y double prime plus 5y equals negative 7, we'll find that 5a equals negative 7, so that a is equal to negative 7/5, and we have our function y of t is c1 cosine root 5t plus c2 sine root 5t minus 7/5. We've successfully solved for y of t, but remember back here, there were two unknown functions. That y was only one of them. Now we need x. There are a couple of different ways we can go with this once we have y, and I'll show you both of them because there are some nuances that I need to talk about. If we look at equation 2, then we can see that 3x plus d plus 2 acting on y is equal to negative 1. And we can find x just by solving for it, right? So x is equal to negative 1/3 minus 1/3 d plus 2 acting on y. We have what y is, and this negative 1/3 d plus 2 acting on y would be what? The derivative of y plus 2 times y, all multiplied by negative 1/3. This is going to be a little tedious, but negative 1/3 dy, so I'm going to differentiate y and at the same time multiply by negative 1/3, is equal to the square root of 5 over 3 c1 sine square root of 5t minus the square root of 5 over 3 c2 cosine square root of 5t. If we then take negative 1/3 times 2 times y, you can confirm that we get negative 2/3 c1 cosine root 5t minus 2/3 c2 sine root 5t plus 14/15. Substituting and collecting like terms is going to give us x is equal to negative 2/3 c1 minus root 5 over 3 c2 cosine root 5t plus square root of 5 over 3 c1 minus 2/3 c2 sine square root of 5 times t plus 3/5. Now, for good form, I'll go ahead and bring y of t down here as well. And that's the solution to the system of equations.